and welcome back to our statistics lecture series for ENIGMA-U. Today, we're going to branch out from our one sample t-tests, and we're going to learn now about the t-test for when we have two independent samples. This is getting into some of the more practical applications of other types of statistics that you might use in your research. And I'm excited to get into this with you. I always do that. I always accidentally click out of it. Okay. We're going to be using pretty much every single symbol we have learned thus far. So this could be a good time to just pause, take a screenshot, write some notes, make sure that you understand what each of these symbols mean and what they represent, and whether they refer to population or samples. We're going to be going back over some of the formulas that we've used again, and the important concepts today we're going to talk about are the t-distribution and degrees of freedom. Emma? Okay, so in order to talk about the two sample t-test, we first need to review what the one sample t-test is. So this is what we spent pretty much all of our lecture last time talking about. The one sample t-test is the hypothesis test that we use when we want to compare data that we've collected from a sample with when we have a known to a population that has a known mean, but an unknown standard deviation. So in other words, we don't know enough about our population to be able to use the z-test that we've talked about before. So we use the t-test, which instead of the population standard deviation, it uses the standard error to calculate our statistic instead. If you remember, the t-statistic, its job is essentially to form a ratio between the actual difference between our sample and population means and comparing it to how much difference is reasonable to expect between our sample and our population means. If this ratio is reasonable, then our null hypothesis is true, our sample mean and our population mean are the same. And if the difference is too much to be reasonable, then we accept our alternative hypothesis, which is that the two means are different. Let's go back to some of our first lectures in this series and review some experimental variables really quickly, what they mean. Experimental variables are going to be important for this lecture and for our next lecture. So let's just take some time to remind ourselves what they are. So in psychology, an experiment involves the purposeful manipulation of one variable, the independent variable, and the measurement or outcome of some other variable, which is going to be our dependent variable. In this way, we can investigate cause and effect, or we can investigate correlation. Our independent variable, like we talked about, is the variable that is manipulated or controlled, whereas the dependent variable is the variable that we measure. We have previously been talking about one sample designs in our lectures. One sample designs are the kind of studies that compare one sample mean to its population mean when we don't know the population standard deviation. That's what we were talking about with the t-statistic so far. Our one sample t-test is referring to the one sample experimental design. The next experimental design, that we're going to present now is the two sample experimental design. This is where instead of comparing one sample mean to its population mean, we're going to compare two different sample means, either drawn from the same population or drawn from two separate populations that have the same mean. And there are two different ways that we can do this. We can either do this through an independent measures test, which is where we have a different or independent sample of individuals used for each treatment condition. We often will call this a between groups design because we use this to compare the difference between two means from two completely separate different groups of participants. An example of this would be a treatment versus a control. You have one group that is your control, and then you have a completely separate group that you do the treatment on, and you compare the means of those two samples. That's an independent measures or between groups design. Whereas a repeated measures or within groups design is when you still have two sample means, but the two means are going to come from the same sample at different time points. In other words, it's when all the individuals in a single sample are measured 2 or more times on your dependent variable. We often will call this a within groups design because you're comparing two means, but like I said, they are all going to be collected from within one group of participants. This is often when we have, for example, baseline and then follow-up testing. So to summarize the experimental designs, we have 3 different types of experimental designs, and we have 3 different t-tests that we use. We've already talked about, and just to summarize, there are 3 types of t-tests. Each is used to compare the 2 means, but what 2 means we're comparing depends on which design we used. The one sample t-test, number 1, is the one we've talked about in the past. This is when we compare the sample mean with the population mean in a one sample design. Like we said before, it's important to remember that the one sample t-test is when we have one sample and we only look at it one time. We're not comparing it to any other samples, and we're not measuring that sample again. One sample, one time. That's why it's called the one sample t-test. The next type of t-test we're going to talk about is the independent t-test. And we use this t-test when we're comparing 2 sample means for a between groups or independent measures design. So this is actually what we're going to talk about today. And it corresponds to this, independent measures. And then the third type of t-test that we're not really going to talk about today is called the paired t-test. And it's when we're comparing 2 sample means again, but from the same sample, from a within groups or repeated measures design. So for the rest of this lecture, like we said, we're just going to focus on the independent t-tests. So the independent t-test, like we said, its goal is the goal of an independent measures research study in which we would use an independent t-test is to evaluate the mean difference between 2 populations or treatment conditions. And we'll differentiate them with the mean from population 1 is going to be called mu1. And the mean from population 2 is mu2. Mu2. A little shout out for the Pokemon fans in here. We're going to use this in situations where we don't have any knowledge about the 2 populations that we're studying. We don't know the mean, we don't know the standard deviation, we don't know anything about any of the population parameters. And what that means is the variance of our population, which is very important in statistics, as we've seen it in pretty much all of our statistics formulas, is that the variance must be estimated from our sample data, not from our population data. Okay, yeah, from population 1, we get sample, or population A, we get sample A, population B, we get sample B. So there are 2 types of research questions in which we would use the independent t-test, and both of them are making a comparison between 2 separate groups of individuals. The first question we could use an independent t-test for is, do the 2 samples, if we're trying to figure out, do the 2 samples come from the same population or do they come from 2 different populations? The other question we could use an independent t-test to figure out is, are the 2 population means from which these samples were drawn the same or are they different? So do the samples come from the same or different populations, or are the 2 populations that we drew the samples from the same or are they different from each other? Just as a callback, because I think it's important to teach the context of what we're learning and how it's different from what we've learned before. In the past couple of lectures, we've been using hypothesis testing to compare sample means to their own population mean, but we've still only ever used one population mean. Now we're introducing a test, the independent t-test, that we can use if we have 2 separate populations that we're trying to compare. We'll talk a little bit more about what the null hypothesis and alternative hypothesis state for an independent t-test, but in general, the null hypothesis states that there's going to be no difference between between the means of our 2 populations, so they're equal to each other. The alternative hypothesis says that there is a difference between the 2 population means. So the formula that we use to calculate the t-statistic for an independent t-test uses the difference between the 2 sample means to evaluate a hypothesis about the difference between the 2 population means. So both of those have to be in our formula. What this t-statistic is going to do is it's going to form a ratio of error, which is what every other t-statistic has done. But this time, the ratio is between the difference in sample means and the difference in population means relative to the amount of error that is expected to occur within these two groups. So our formula, by extension, in the numerator has the difference between the two sample means, which we get from our sample data, and the difference between the two population means, which we get from the null hypothesis. And then you find the difference between those, the difference between the differences. And then the denominator is an estimated standard error of the difference in the sample means. It's not the standard error of group of sample 1 minus the standard error of group 2. It is the standard error of the difference in sample means. Those parentheses are important. Basically what this does is it's just gonna, like it says here, it's just gonna estimate the average amount of error that is expected when you use sample statistics to predict population parameters. That's what this is telling us. So let's talk a little bit more before we move on about this denominator here, the estimated sample standard error. Excuse me. So it's the denominator in our last formula. And the important difference about the estimated standard error in an independent t-test is that for the first time ever, we have two sources of error, not just one. Because we're taking two sample means that each represent their own population mean, and each of those relationships has some error. The difference when we're using the mean of sample 1 to estimate the mean of population 1, that's some error. And then there's another error when we use the mean of sample 2 to estimate the mean of population 2. That's two separate sources of error. So the amount of error associated with each sample mean is going to be measured by the estimated standard error of that mean. Estimated standard error of mean 1, estimated standard error of mean 2. Just in summary here, this is kind of what we've already said. For the independent measures t-statistic, we want to know the amount of error that is involved in using two sample means to approximate two population means. So we need to find some way to combine the individual errors to find the total estimated standard error of the difference between the two sample means. There are two different formulas that we can use for this, and they depend on whether or not we can estimate the variances. So if the samples are the same size, then we're going to find the error from each of the samples separately, and we're going to add the two errors together. Estimated error for sample 1, estimated error for sample 2, and we just add those bad boys together. That's all it is. And that's how we can combine them here under the same square root. And the reason we can do this is because the formula treats the two sample variances equally. Because they're the same, and we're using the sample size to determine the variance here, which is not necessary, which we've talked about isn't the best, but as a general rule of thumb is okay. But because of that, if our sample sizes are different, we can't just add the standard errors together. So instead, we need to use something called the pooled variance, which instead of being just a standard error is actually going to be a weighted average. So it allows whichever sample is larger, or in other words, whichever sample has more degrees of freedom, to carry more weight in the final value. And to figure that out, we're going to use the sum of squares and the degrees of freedom. We're going to add them together, and that's the pooled variance. So that's what our formula looks like if we have two separate sample sizes. Same sample size, different sample sizes. The only difference is with same sample size, we can use the standard error in the numerator. With different sample sizes, we have to use the pooled variance. And what we're doing by using the pooled variance is just when we have an unequal sample size, we can get an unbiased measure of the estimated standard of the difference between the sample means. As a general rule, whenever you see degrees of freedom, we're trying to make an unbiased statistic. Yes. However, I will note before we go into this example that it's best if we just use this formula for determining the standard error of the difference, even if we have equal sample sizes. We generally just use this one just to be safe. So here's an example. So if we have equal sample sizes, the sample size is 6 for both of these. We're still going to use the pooled variance. We're going to calculate the pooled variance for sample 1 and for sample 2, and then we'll add them together and we get 8. If we have unequal sample sizes, so sample 1 has 3, whereas sample 2 has 9, we're going to use the same formula here, the pooled variance, and then we're going to add them together and we get 2.875. What I want to point out here is that we can see that when we have equal sample sizes, your pooled variance is going to be an average of the two standard errors exactly. And the reason for that is because both of the samples are being weighed equally. However, if you have unequal sample sizes, when you use this pooled variance formula, the estimated standard error of the difference is going to be much, much closer to the sample that has the bigger sample size. Okay, just a good note there. So here is a summary table of some of the elements of a t-statistic. Feel free to spend some time with this. Make sure you understand the differences between the one sample t-test that we talked about last time and the independent measures t-test that we're talking about today. I'm not going to go over it too much because we have already gone over this, but the one thing that I will use this to point out is here's our t-statistic formula for an independent measures test. Remember, we take the difference between the sample means and the difference between the population means, and we find the difference between them. However, according to the null hypothesis of an independent measures t-test, the difference between the two population means should be 0. And because of that, we usually just write the t-statistic formula like this. We just say this is 0, and we just write it like this. Okay. Let's go over, before we do an example, let's go over how we find the t-critical values for our independent t-test. As you may remember from the last lecture, degrees of freedom is a very important factor when we're trying to find t-critical values. And here, because we have two different samples that we're looking at, we're going to add their degrees of freedom together. So you're going to take the degrees of freedom from sample 1 and add it to the degrees of freedom for sample 2, which if you distribute this out, is just going to be the two sample sizes added together minus 2 instead of minus 1. And as before, just like in our one sample t-test, in order to decide whether or not we want to reject the null hypothesis, we're going to compare our t-statistic to our critical values. And if our observed t-statistic is inside the critical zone, it's either lower than the lower value or higher than the higher critical value, then we are going to reject the null hypothesis because we're saying that the difference between the means that we're seeing is too big to be reasonable. So let's look at testing a hypothesis with an independent t-test. So here are the steps. Very similar to all of the other steps that we've used for hypothesis testing. The actual hypotheses and the formulas are the only things that change. So as a reminder, our independent t-test is going to use data from two separate samples to decide whether there's a significant difference between two population means or two treatment conditions. Our hypotheses, the first step is to state our hypotheses and select our alpha level, as always. Our null hypothesis in an independent t-test is that the two population means have no difference between them. The alternative hypothesis is that there is a difference between the two population means. The degrees of freedom, then the second step is going to be, and the alpha level is still generally just 0.05 or 0.01 or 0.001. Second step, compute the degrees of freedom. We know how to do that with this new formula. The third step is to obtain the data and then to compute our test statistic. And we'll go over how to do that in the next slide. And then we make a decision. Really quickly, let's talk about when we would use a two-tailed test versus a one-tailed test with an independent t-test. The two-tailed tests are going to be called difference hypotheses because all we're doing is testing whether group 1 has a different mean than group 2. The null hypothesis is that there is no difference between the means. The alternative hypothesis is that there is a difference. No direction is mentioned here. In a difference hypothesis or two-tailed test, we have two t critical values, one positive and one negative, And our observed t-statistic needs to fall in the critical zone, so outside, either higher than our positive t-critical value or lower than our negative t-critical value. An example of a situation in which you would use this is if you were testing whether room temperature changes test performance. So you'd expect the first group to have a different mean score than our second group, the treated group, but you don't know what direction those scores are going to go. Excuse me for one moment. Okay. There are one-tail tests, on the other hand, are not difference hypotheses, but they're directional hypotheses because they specify a direction. Let's look at the positive one-tailed test first. When you have a positive one-tailed test, you're testing whether group 1 has a higher mean than group 2, and that order is very important. Your alternative hypothesis is just that the mean of group 1 is greater than the mean of group 2, whereas your null is that the mean of group 1 is less than or equal to the mean of group 2. Even if your means are the same, you do not reject the null hypothesis. In a directional t-test, the means actually have to be more or less, depending on which one you're using. So in a positive t-test, you have one t-critical value, and it's on the positive side, and the t-statistic needs to fall to the right, so more positive than your t-critical value. And an example of this could be if you're testing whether therapy lowers depression. So you would expect the first group, your control, to have a higher mean depression score than the second group, the one that received the therapy. A negative one-tailed test, on the other hand, says that group 1 should have a lower mean than group 2. That's your alternative hypothesis, that the mean of group 1 is less than the mean of group 2. And your null hypothesis is that the mean of group 1 is greater than or equal to the mean of group 2. You're going to have one t-critical value again, one-tailed test. It's going to be on the negative side this time, and your observed t-statistic needs to fall within the negative tail, so to the left of the critical region. An example of this is if you were going to be testing whether tutoring increases GPA. So you would expect the first group, the control group, to have a lower mean GPA than your treated group that received the tutoring. So let's look at an example really fast. So an example in which we would use an independent t-test is if a researcher was interested in determining whether or not playing video games for 20 or more hours a week in high school has an effect on SAT scores. That's our question. So in other words, our research question is there a significant difference, in SAT scores between those who played video games for 20 or more hours per week and those who did not? Notice that we said, is there a significant difference? We didn't specify a direction. So right away in our heads, we could say, okay, this is going to be a two-tailed test, not a one-tail, because we're just looking for a difference, not a direction. The research design that you could use is a between groups independent measure study, since we're talking about independent t-tests. Your independent variable is going to be the hours that they spent playing video games in high school. And then the dependent variable, the one you're measuring, is their SAT scores. So the method that we're going to use is we're going to obtain the SAT scores for two different samples. Sample 1 is going to be 20 adults who reported playing video games for less than 20 hours per week in high school. We're going to collect all their SAT scores. Group 2 is adults who reported playing 20 or more hours of video games in high school. We collect the sample mean, sample standard deviation, sample estimated standard error, and the sum of the squared standard deviations from the mean. Okay, let's get into this. So step 1 is going to be to state our hypotheses and select our alpha level. Alpha level, 0.05. That's what we're using. According to the literature, that's fine. The null hypothesis, remember, is that the two population means are the same. There's no difference. In other words, in the context of this example, there's no difference in the mean SAT scores between people who played less than 20 hours of video games in high school and those who played 20 or more hours of video games in high school. No difference in their mean SAT scores. The alternative hypothesis, on the other hand, is that there is a difference in their SAT scores, depending on how many hours of video games they played per week. Step 2 is going to be to compute our degrees of freedom and then locate our critical region. So the degrees of freedom formula right here tells us that our degrees of freedom for this example is 38. And since our alpha level, we're using a two-tailed test, and our alpha level is going to be 0.05 in both tails combined, we're going to use this column and this column to get these critical values. Note here, for degrees of freedom, you always round up, you never round down. So even if our degrees of freedom turned out to be 32, even though 32 is closer to 30, you always are going to round up. So even if it was 32, we would still use this 40 column right here. So our T critical values are going to be negative 2.021 and positive 2.021. Step 3 is going to be to obtain our data and compute our test statistic. So in order to get our test statistic, we need to do 3 steps. Number 1, we need to find our pooled variance. Number 2, we're going to use our pooled variance to find our estimated standard error of the difference, this guy, our denominator. And then step 3 is we're going to use that denominator to calculate the T statistic. So number 1, we're going to find the pooled variance. If you want, you can pause the video and try to figure this out on your own, but I'm just going to breeze through it right now. So we're going to find the pooled variance here, and using our test statistics, we get this value here. Then we're going to use this 34,973. We're going to put it in the formula for our estimated standard error of the difference right here. Boom, bam. The estimated standard error of the difference, so our denominator is going to be 59.14. And we put that right here in our denominator of the T statistic. Thus, our T statistic, our observed T value, is going to be 2.122. Now, if you remember, our critical values were 2.021. Since our observed T statistic is within the critical zone, it's higher than our positive T critical value, we're going to reject the null hypothesis and say that there is a significant difference in the SAT scores of those who played video games less than 20 hours per week in high school and those who played video games for 20 hours or more per week in high school. So we're going to stop right here. And then in our next lecture, we're going to talk about how to report things like effect size and confidence interval for an independent t-test.